Imagine a war where machines can calculate trajectories, process radar inputs, and generate predictions, but cannot react in real time. Data arrives continuously, faster than human operators can interpret it, yet existing memory systems are unstable, slow, or unreliable. Information fades, resets, or corrupts before it can guide action. In this environment, automation fails not because logic is wrong, but because machines cannot remember reliably from one moment to the next. J. Forrester solved this problem by inventing magnetic core memory, the first computer memory capable of storing information accurately, updating it continuously, and operating without failure under constant load. This invention transformed computers from calculation devices into real-time control systems, making automated air defense and large-scale military decision systems possible, before combat ever began. J. Wright Forrester was born on July 14, 1918, in Anselmo, Nebraska, United States. He grew up in a rural environment during a period when electricity, radio, and mechanization were spreading unevenly across the country. Unlike engineers raised in industrial centers, Forrester's early surroundings emphasized practical problem-solving and self-reliance, rather than exposure to large technical institutions. His family background was not rooted in military or industrial engineering. There is no indication that his parents worked in advanced technical fields. His early education followed the standard American school system, where he demonstrated strong aptitude in mathematics and mechanical reasoning. From an early stage, he showed interest in how systems functioned as a whole rather than as isolated components. Forrester pursued higher education in electrical engineering. His academic training emphasized circuits, control systems, and applied electronics. He was educated to analyze how machines behave under continuous operation, how feedback affects stability, and how errors propagate through complex systems. This focus distinguished him from engineers oriented toward short, discrete calculations. After completing his studies, Forrester joined the Massachusetts Institute of Technology, MIT. At MIT, he entered research environments concerned with real-world engineering constraints rather than theoretical models alone. His early work involved electronic systems that had to operate reliably over extended periods, exposing him to the limitations of existing technologies when used under constant load. During this period, engineers faced growing challenges related to automation and control. Systems were becoming faster, larger, and more interconnected, but available electronic components were unreliable when operated continuously. Memory devices in particular were unstable, prone to failure, and unsuitable for real-time applications. These limitations constrained the development of systems that needed to track changing conditions rather than perform isolated computations. Forrester became involved in projects addressing these limitations. His work shifted toward understanding how information could be stored, updated, and retrieved reliably while systems remained active. Rather than focusing on individual calculations, he concentrated on continuity, persistence, and system stability. These concerns would soon become central to his most important contributions. As military interest in automated control increased during and immediately after World War II, MIT expanded research into systems capable of processing data continuously. Forrester's background in electrical engineering and control positioned him to address a problem that others avoided: how to build machines that could operate without interruption while maintaining accurate internal state. This challenge marked the transition from calculation-focused machines to systems designed for real-time decision support. At this stage, Forrester was not designing weapons. He was addressing a foundational engineering problem: how to make machines remember reliably while the world around them changed. Solving this problem would determine whether automation could move beyond calculation and into control. As Forrester's work at MIT progressed, his focus shifted from individual electronic components to system behavior under continuous operation. Existing machines performed calculations in batches. They started, processed a task, and stopped. This mode of operation was incompatible with emerging military and industrial needs, where information changed continuously and delays accumulated into failure. In research environments linked to wartime and immediate post-war requirements, engineers attempted to adapt existing computing technologies to control problems. These efforts exposed a fundamental limitation. Vacuum tube-based memory systems were unreliable, slow to access, and prone to failure under constant use. Systems could compute, but they could not maintain a stable internal state while responding to live input. Forrester's work increasingly addressed this limitation. He analysed how instability in memory disrupted feedback loops and caused control systems to behave unpredictably. Without persistent and accurate memory, machines could not track targets, maintain trajectories, or support decision-making over time. This problem was not abstract. It emerged repeatedly when systems were tested outside laboratory conditions. Rather than attempting incremental improvements to existing memory technologies, Forrester began exploring alternative approaches to information storage. His objective was not increased capacity, but reliability and speed under continuous load. Memory had to retain information without degradation, update rapidly, and function independently of fragile timing constraints. This line of work positioned Forrester at the intersection of computation and control. He was no longer addressing how fast a machine could calculate, but whether it could remain coherent while interacting with a changing environment. This distinction marked a transition in engineering priorities. Machines designed for calculation were insufficient. Systems designed for control required a different architecture. By the end of this phase, Forrester's work had clearly moved beyond conventional computing problems. He was preparing to address a foundational requirement for real-time systems, stable memory that could support continuous operation. This requirement would soon lead directly to his most significant invention. The engineering problem J. Forrester faced was not how to make computers faster, but how to make them reliable under continuous operation. Early computers relied on memory systems that were unsuitable for real-time use. Delay lines, electrostatic storage, and rotating drums were sensitive to noise, temperature, and timing errors. They failed frequently when machines were required to run continuously and respond to changing input. Forrester recognized that real-time systems required a different type of memory. Information had to be stored without decay, accessed instantly, and updated repeatedly without disrupting system stability. Memory could no longer be treated as a temporary buffer. It had to function as a persistent internal state that machines could rely on while interacting with the external world. To address this problem, Forrester developed magnetic core memory. The system used small magnetic rings called cores, threaded with wires. Each core stored a single bit of information based on its magnetic orientation. This approach allowed memory to retain data without power, resist electrical noise, and operate at high speed. Unlike previous memory technologies, magnetic core memory could be read and written reliably millions of times. Magnetic core memory solved multiple problems simultaneously. It eliminated the fragility of earlier storage methods. It provided predictable access times, which were essential for real-time control. It allowed machines to maintain accurate internal state while processing continuous streams of input. For the first time, memory behavior could be trusted under sustained load. This invention was implemented in the Whirlwind computer at MIT. Whirlwind was not designed as a calculator. It was built to process radar data continuously and support interactive control. The integration of magnetic core memory transformed Whirlwind into the first computer capable of real-time operation at scale. Systems could now track objects, update predictions, and respond immediately as conditions changed. The impact of this development extended beyond a single machine. Magnetic core memory became the standard memory technology for computers used in military, scientific, and industrial systems for decades. It enabled the construction of large-scale command and control systems where failure or delay could not be tolerated. Forrester's invention changed the role of computers in military systems. Machines were no longer limited to offline calculation. They became components of operational systems that supported decision-making before engagement. Real-time memory allowed automation to function reliably in environments where human response alone was insufficient. By solving the memory problem, Forrester removed a critical barrier to real-time control. His work made it possible to build systems that could absorb continuous data, maintain coherence, and act predictably. This capability would soon become central to air defense, command networks, and the emerging field of automated control systems. The introduction of reliable real-time memory changed how military systems could be designed. With magnetic core memory in place, computers were no longer constrained to isolated calculations. They could now operate continuously, maintain internal state, and respond immediately to incoming data. This capability was essential for systems that needed to track fast-moving threats rather than analyze past events. The Whirlwind computer demonstrated this shift clearly. Designed to process radar data in real time, Whirlwind could receive continuous input, update tracking information, and present actionable outputs without interruption. This was not an incremental improvement. It represented a fundamental change in how machines interacted with dynamic environments. Decisions could now be supported while situations were still unfolding. These capabilities directly influenced the development of large-scale air defense systems in the United States. Radar stations generated massive streams of data that could not be handled effectively by human operators alone. Real-time computers, equipped with reliable memory, were required to correlate tracks, predict movement, and support coordinated response across wide geographic areas. Forrester's work became foundational to the SAGE, semi-automatic ground environment system. SAGE integrated radar networks, communication lines, and computers into a unified command structure. Its purpose was not to fire weapons automatically, but to reduce uncertainty and reaction time. By maintaining continuous situational awareness, SAGE allowed commanders to make informed decisions before enemy aircraft reached critical targets. The effectiveness of these systems depended on memory stability. Without persistent and reliable memory, tracking would collapse, predictions would reset, and coordination would fail. Magnetic core memory ensured that information remained coherent as data flowed continuously. This reliability allowed air defense systems to scale without becoming unstable under load. Although SAGE reached full operational maturity after World War II, its foundations were laid during and immediately after the war. The engineering problems it solved were direct extensions of wartime requirements: early warning, rapid coordination, and decision-making under time pressure. Forrester's invention addressed these needs at their root. The broader impact of Forrester's work extended beyond air defense. Real-time computing became essential in navigation, industrial control, and communication systems. In each case, the same principle applied. Machines had to remember accurately while interacting continuously with the world. This requirement defined modern control systems. J. Forrester did not design weapons, aircraft, or missiles. He designed the internal capability that allowed complex systems to function reliably under pressure. By enabling machines to maintain stable memory in real time, he shifted the balance from reactive response to informed anticipation. This change affected how conflicts were prepared for, long before combat occurred.